then do the same thing on another metal substrate and bring them into contact and change rotation angle. The energy input in terms of dissipation from friction and the speed without seizing could be remarkably high. So there's a fascinating connection between fundamental science of these sorts of length scales and possibilities for manufacturing in terms of components that are rubbing against each other in topology.
Did you move them with a GM?
We moved them with an AFM.
An AFM, sorry.
That's right. No, that's a good point. So part of it was this top-down rubbing silicon wafers, and part of them we showed we could dislodge with an AFM. It was actually that clued Quan Shi and his team in, because that only happens in certain locations within the graphite. So there's probably some sort of aspect of the structure that makes
this was in a vacuum.
These experiments were actually just in ambient pulse.
They're in air.
Yeah.
Because in a vacuum, they probably didn't move.
That's right. So that's another interesting point that Gary is alluding to, which means that the mechanics of graphite is still not understood. Is you might think that graphite is a very good lubricant. It's in our pencils with binder material, and it is actually used as a lubricating system, but never in vacuum. And the reason is still not understood. It's still debated in the literature. It's thought that one model proposed by some is that at the neighboring layers in air, you have water molecules and other molecules that might behave like molecular ball bearings. And sort of, as you're going to slide, those can wedge between and help to cleave the graphite on the nano scale. But in vacuum, you don't have those. However, this model is not completely conceptual.
You can test this. This particularly interests me.
Just provide me funding. I'm kidding, but only have to. Because it's a great...
I just provide the idea, you can write a paper.
No, we've been thinking about this for a long time.
I mean, it would be interesting to see sodium interpolated in there as well.
Sure, absolutely. To put interpolates in and look at the mechanics is now within access, I would say, with the manipulators and so on. So this is an extremely interesting issue in terms of fracture mechanics, because I think the models in terms of cleavage of graphite are still under active discussion. It's not a solved problem, particularly for different environments like that.
Well, you might tell them how it was discovered, you know? Do you know?
This group.
This interpolation, this sliding? It was discovered during the war, and as the airplanes went up to higher and higher altitude to shoot down the bombers, they discovered that the graphite brushes on the motors burnt out because they became abrasive. And so they discovered that at high altitude, it was probably outgassing, and that you cannot use graphite on the shuttle. You use molybdenum sulfide. So all the textbooks are wrong.
That's a great story.
Chemistry. And they're still 65 years after the discovery. Almost every textbook will say that graphite is a lubricant because of weak interlayer forces. That's wrong. That's shown. Right here.
Yeah, no, that's a great. I didn't know that.
No, it's a good story.
Yeah.
Okay. It's a Spitfire stuff.
We were just at.
Well, the bombers came in and they had to go to higher altitude. And as they went to higher altitude, the brushes, they actually became abrasive and wore out. And so
we were at Nanotube 2011, so this is a trip within a trip.
Oh, yeah.
And indeed, we were at the Air Museum for the banquet dinner, and saw a lot of the beautiful Spitfires and so on. We got a wonderful.
When you say that we don't know the mechanics of graphite, what do you mean?
What I mean is, it's not that we don't know some things, but there is still debate in the literature about this mechanism of cleavage for sliding of layers. And given Quan Shi Zheng's recent work at Tsinghua University, I would say there's still open questions about what happens indeed when you anisorate the layers, or when you're trying to clean material which is able stacked or not able stacked. So that science is still developing. And certainly we don't know everything we'd like to know about fracture mechanics So, in this paper, just to give you a little bit of history, we did also mention that more extensive rubbing, would probably lead to graphene. And it's a little known fact that in the Science paper in 2004, published by the team from the University of Manchester, if you carefully read the supplemental, the first approach they used, and therefore published in that paper, was the fillers. And then later they realized, I think fortunately, that the fillers slowed them down in a sense. They could just use Scotch tape without making the fillers and get individual layers of graphene. And then the field, particularly in physics, really took off. But they were inspired by our work, which makes me happy. That's kind of a fun thing about science, is seeing your work influence other people. I'll tell you a little story sort of related to philosophy. It connects with my father, who did high-pressure physics at Cornell. So achieved the highest pressures that have ever been achieved using diamond anvil cells, and higher pressures than at the center of the Earth. Well, I never knew, and neither did my four brothers, that my father really loved mathematics. But he grew up on a farm in Indiana and did the pragmatic thing of first going into engineering. And he got his PhD with Henry Iron and learned some physical chemistry and studied the mechanics of wool, hydrogen bonding. And then he went off to Cornell and started his career as a metallurgist, switching. And then material science came into being. He joined one of the first departments in the world and started doing material science. So he had this love of number theory, and he was actually very good at it off the farm at Purdue University, but he left it behind for 50 years. So when he became an emeritus professor, he started furiously working on some aspects of Fermat's theorem. And he made great progress and actually got a paper passed through the editor of the American Journal of Mathematics, but finally it was rejected. So after 4 years of very hard work, he said, I understand why science moves so fast. We never have to get it completely right. But in mathematics, you have to have a perfect proof, even if everyone kind of knows probably mostly right, and then they don't publish it. So in science, that's often the case that, of course, we've overlooked something. And science is self-correcting, other people do research that we realize we missed something. So I just want to say that there are some good reviews, not only by my own research group, but if you look on my website, you'll find some very nice reviews about the history of graphene and chemically modified graphenes, just in case that's of interest to you. So we might have something like this staircase in terms of discovery, and these were the very important recent experiments led to the Nobel Prize for Andre Geim and Kasia Oslov. And then we continue, and other people do, trying to expand the repertoire of materials available. So one dream that I have, and other people do too, is to try to make graphene or ultra-thin graphite or multi-layered graphene such that we can make it and spool it up, something like we do metal foil or plastic foil. So we could make kilometer lengths of the material and have that useful for many applications, let alone for science. And so, well, sometimes in the United States and elsewhere, of course, if you have intellectual property, then people want to invest money so we can start small companies. So now let me tell you something about the growth, because I think it's quite important for you to appreciate what's happening with carbon, with different sorts of metals, in terms of the growth. And there are lots of fascinating issues in terms of mechanics that come up here that haven't been investigated yet. I think people are looking at it in terms of theory and modeling and experiment. So the binary phase diagrams of different metals with carbon are very useful as guideposts. The thermodynamics is, in other words, important. We might, in our growth, have kinetic control, not thermodynamic control, but at least thermodynamics supply certain constraints. So for example, if we consider processing at 1,000 degrees C, you can see for some of the systems like platinum and nickel that the solubility of carbon in those metals is quite high at thermodynamic equilibrium. In nickel at 1,000 degrees C, it's 1 atomic percent. So there's a large amount of carbon actually in the nickel at equilibrium. But in copper, the solubility is very low, and I would argue it might even be 0 in data that I will show you. But there are several papers in the literature that talk about the solubility being a few parts per million or about 150 parts per million at 1,000 degrees Celsius. So suppose we are sitting around thinking about how to grow graphene on a metal, and we want to use a metal foil, because metal foils are available in very large areas, such as copper or other choices. Well, typical thicknesses of metal foils, just so that they would be stable, are sort of tens of microns in thickness. If I use a nickel foil, tens of microns in thickness, so much carbon might dissolve into the nickel that I would get graphite on the surface. And in fact, we've done that. But our thinking was if we took copper, then at least the solubility is projected to be so low that maybe a standard copper foil, 100 microns in thickness, might give us graphene when we cool down. So as you cool down, I'll show it with nickel, the solubility drops. So by the time you get to 300 Kelvin, if you maintain thermodynamic equilibrium, there's no more carbon in the nickel. It's all come to the surfaces and precipitated out. So two choices could be copper and nickel in terms of cost and large area processing. We have a different situation in terms of this solubility. Another fascinating thing about copper that some of you may know, Dr. Luigi Colombo, my collaborator from Texas Instruments, knew this. Copper evolves very large grains very easily. So we start with copper foil that might have grain size of just tens of microns that we get from somebody, company, etc. And if you heat it up to 1,000 degrees C under vacuum or inner environment like argon gas, you can get centimeter grains very easily. So you have single crystal regions that are centimeter grains. That turns out not to be true for nickel. Nickel always maintains a relatively small grain size. So it might end up being important to have single crystal regions that are very large to grow graphene. That's still being investigated. So we've been using both cold wall and hot wall systems. This is a so-called hot wall system. It's a simple tube furnace. And this is thermal chemical vapor deposition precursors like methane. So we have a simple heating regimen under hydrogen. And the goal is to strip off the oxide layer on the copper to expose the bare copper surface. And then to find out, will the methane decompose and leave active carbon species that will surface diffuse or go down into the bulk copper? Our original thinking was, per that binary phase diagram, that they would go down into the copper. And then when we cool down, growth would be occurring by precipitation from the bulk. But the picture is different because we learned differently that actually growth occurs at temperature such as 1,000 degrees C, and the growth is entirely surface mediated. There's no dissolution, dissolving of carbon atoms down into the bulk copper. And I'll prove that in a few slides by a new experimental method we developed. So this led to the first example of growth of clean monolayer graphene over a large area. And it's had a very significant impact worldwide. And so we were sort of fortunate that the growth was a different mechanism than we were thinking it might be from thermodynamic binary phase diagrams. And after you grow graphene on copper, it turns out mechanics is challenging. Even just the surface tension of water, when we are dissolving away the copper, if we don't mechanically support the graphene, for example, with thin polymer film, surface tension effects from these aqueous etchants, like iron trichloride in water, will break the graphene apart. So there are probably small defects at the edges that are stress concentrators that the surface tension forces are acting on to fracture the graphene. So it was actually Chunky Yu at the University of Houston who first used PMMA on multilayer graphene grown on nickel and dissolved the underlying metal. So that was a very important approach that we've adopted with copper. And so there's a great deal of interest right now in transfer. Transfer is not very good. There are probably some experts in the audience on delamination. How do you account for surface adhesion of a film on a substrate and correctly delaminate it without breaking it. I would say what we're doing right now is not very elegant, but we're doing the best we can, and so is everyone else. We're dissolving away the substrate that we glue on. Not a very satisfactory situation for manufacturing. In manufacturing, we'd like to have a belt of, say, copper, and run it around through a hot zone where we have these gases, grow the graphene, and then delaminate it, and pick it up, maybe roll to roll, and then use the copper over and over. But now we're dissolving the copper away. So there's a lot of fascinating issues that are not understood now in terms of the mechanics of the adhesion of the graphene to the underlying metal, and how to loosen that relatively moderate adhesion, if you will. We don't even know the energetics at this time, so that we could delaminate it without dissolving the copper. But with that approach, you can then transfer the graphene to substrates like glass or PDMS polymer, and you can dissolve away the polymer that you used here, like PMMA with acetone. There's always some residue that causes problems in terms of electronics and so on. So there are a lot of challenging processing issues to get back to pristine graphene that might be needed, for certain fundamental studies or for applications. So now I'm going to show you an experiment that addresses this issue of whether the carbon was going down into the copper and then coming out during cooling. But we've already had a pretty good idea that it wasn't. In that first paper, this paper we published in Science in 2009, we had used different thicknesses of copper foil, 25 micron, 50, 125. We've always got monolayer graphene. So clearly, that suggests that it wasn't by precipitation, because the 125 micron thick would appear thicker, like bilayer, trilayer, etc. So we invented this approach where we dose with isotopically labeled methane. And Harry had mentioned the benefit of using C13. There's a great benefit here in understanding growth kinetics and also the mechanism of growth. So in this regime where we first introduced the methane before cool down, we're introducing C13 methane for 1 minute, and then I'm calling this C12, but it's just normal methane. So there's only 1.1% C13, and so on. Every minute, our flow controllers are switching between the two types of methane. We can then use micro-Raman mapping microscopy, and it turns out that pure C13 graphene has a G-band in the Raman spectra, which is shifted dramatically from normal graphene by 60 wave numbers. So then it's trivial with this sort of instrument to assign a spectral bandwidth that is only collecting, for example, the peak at 1520 and not the peak at 1580 that's given normal graphene. And by doing that, we get a color-coded map in which this region here, for example, is C13 graphene. This is normal graphene, or essentially C12. This region here is C13, and growth was terminated after the third minute. Okay. So we end up with nucleation occurring in different spots on the copper, islands growing outward and then knitting together. And there's no more active copper surface, and growth stops at a monolayer. So this is very valuable. It shows us the grain size. It shows us what the grain boundaries look like. And we can also do something called D-band mapping. D-band shows up in a different location, actually around 1340 wave number. And it's an indication of defects such as wrinkles in the film, and also can show where the grain boundaries are. So soon we'll talk about what's the structure of the grain boundaries, and we'll talk about pentagons and heptagons, as Harry did with pentagons for C60. What's kind of fascinating also is the presence of these wrinkles. Why do wrinkles show up? They show up because the coefficient of thermal expansion of copper is much, much larger than that of graphite. In fact, graphite is a very unusual material. Between about room temperature and 700 Kelvin, graphite has a negative coefficient of thermal expansion. So as you heat it up, it contracts laterally. And graphene actually does the same thing at room temperature. It it's not yet mapped entirely in terms of the temperature dependence the way graphite has been.
It should give you some spontaneous examination.
Right, or a tremendous stress.
In this the temperature range again, what's
For graphite, it's 300 to 700 K.
the graphite?
In graphite.
What about the graphene?
In graphene, it's apparently negative. I'll show some data.
Is that in free space or
Yeah, it's when it's suspended. But it's,
over what temperature range?
the temperature range for graphene is not completely mapped out.
It's over 100 degrees.
Oh, I think so, yeah. No. So Jeannie Lau's group at UC Riverside has generated in graphene, suspended graphene examples where they get this beautiful crippling effect, which is a consequence of it having a negative
Is
C.
that two-dimensionally isotropic or do we know?
It is
We know
considered,
it's
it's considered to be 2D isotropic. Yeah. So these wrinkles indeed appear because as we're cooling the copper, or it happens also for nickel and the other metals as well, at such a high temperature, the delta CTE, coefficient of thermal expansion change, is quite large. And so the copper is contracting and the graphene doesn't want to. And so the stress buildup is such that it does de-adhere and you end up with these beautiful wrinkling patterns. I consider them to be beautiful for a couple of reasons. One is when we look at this material in scanning electron microscopy, the wrinkles are actually our way of identifying the presence of monolayer graphene before we go into Raman. And the wrinkles, remarkably, if this is a grain boundary in the copper right here, the wrinkles typically run by and large orthogonal, so that the graphene grains, remarkably, in copper will span the grain boundaries in the underlying copper grains. So copper is a sort of fascinating system compared to some of the other metals. Per ab initio calculations by theoreticians, copper and the other noble metals such as silver and gold are considered to be physically interacting. There's no chemical interaction at all in terms of the bonding orbitals. In contrast, like I told you for nickel, there's significant overlap in this chemisorption. And so copper in some sense is a more forgiving system for growth. It doesn't have to necessarily be epitaxial growth and lattice match. In some sense, the theory that's being developed for our experiments, the carbon species kind of float around in the copper and move very readily on it, and they're more likely to interact with each other than with the underlying copper. So there are wrinkles, and the mechanics of those are not yet understood. So people, I think, are beginning to model that, such as Bui Tuan at the University of Texas at Austin and others. It's still a quite exciting area. I can tell you that we've actually observed fracture. When we have much, much thicker films where we've grown on nickel, the wrinkles, the stress buildup is so large that when you look at cross-section TEM, you can see that some of the layers are actually broken. So the stresses can be quite large that are built up. Excuse me. So this picture that we have for two different systems, we did the experiment on nickel and we get one color. And the reason why we get one color instead of two colors is because we get isotopically scrambled graphene because the mechanism is entirely different. The atoms go down into the nickel, they move around and diffuse, and when they precipitate out upon cool down, of course they're isotopically scrambled. Whereas this is the picture with copper where we have surface moving from the home. So both techniques are valuable and both are interesting. Both are being studied. Particularly if we want to make multi-layer graphene, we're going to use copper that favors the monolayer growth. We're going to have to invent different parameter spaces to try to grow the next additional layers. Maybe switch the precursor from very stable methane to something that's very unstable like acetylene and so on. But if we're going to try to grow multi-layer by precipitation, we have these choices like we know. And we might, by kinetic control, quench even with the thick nickel piece where we might have saturated the carbon. So most of the carbon will stay in the nickel and end up with a thin layer of graphite. Multi-layer. So some of you might be aware in terms of phonon physics that the thermal conductivity of isotopically pure take diamond, normal diamond, and look at the thermal conductivity, and then you make diamond by using C12 pure precursor, the thermal conductivity can be 50% higher at room temperature. It's quite remarkable. So 1.1% C13 in the tetrahedral lattice causes significant phonon scattering, phonon isotope scattering. So we might expect that the same thing will be true with graphene, and we have a paper submitted to Nature Materials about that, that's addressing that issue by having made C12 pure and then 50-50 C13 and so C13 pures. So I think that there will be actually very interesting fundamental studies with these isotopically labeled materials. They are useful for mechanics, as I will show you later, because they let us identify where the grain boundaries are optically, instead of always having to use a very complicated technique like transmission electron microscopy. Now I'm going to show you some fun results. I always encourage my group members to be independent and do the things that they think might work. And so my postdoc just got this funny idea of just folding over the copper foil or crimping it around its edges to make a little pocket on the inside. Now it still leaks, so the methane can go inside this and the hydrogen also, but the conditions inside this enclosure are quite different than they are on the outside. So the graphene we grow on the outside is quite different than the graphene we grow on the inside. We call this a pocket within the enclosure. And we end up with kinetically controlled growth inside. And we've gone in just a couple of years from grain size of a few microns up to millimeters now through playing around with the parameters. So I think you can appreciate it in terms of strength and perhaps thermal conductivity. At some point, grain size is very important because of weakness at the grain boundaries or scattering by phonons at the grain boundaries. So one of our interests is to try to grow the largest grain material we can. And in this work, we ended up observing that we had these, but we had to question whether they were or weren't single. And one thing we did that, again, uses this isotopic labeling is, let's talk about what Gary had mentioned, a zipper mechanism. I can tell you that the copper surface is very rough. It's highly faceted at 1,000 degrees Celsius. And we have the question, when we have these two different lobes, like this here and this here, and they're growing outward, in the regions where they merge as they grow outward, what's happening? Do we have a defect along that line, for example, and therefore many, many defective regions as this grows? Or does somehow it join in such a way that we have perfect hexagons along that line? So one way of evaluating that was to do this isotopic labeling again and color code where the joining line is, so we can identify it very, very accurately. As I'm showing you here, this is exactly where that region merges. And so if we have pentagons and heptagons along that line, we would expect to see a D beam in Raman. But when we look with Raman, we see no D band at all. Completely absent. And so that suggests to me, although I don't have proof of it, that the growth mechanism might be this sort of zippering mechanism. I have a hard time understanding how when I have two surfaces in completely different locations, which is what I expect at 1,000 degrees Celsius, somehow these surfaces are going to merge without there being a zippering back here. Okay, so I think it's zippering outward, but proving that would be a very fascinating challenge. We also benefited here through collaboration with colleagues at...
What temperature was that going on?
So it's growing at 1040 C. And the melting temperature...
10-4, that's quite high.
1,040. And the melting temperature of copper is 1,080.
Difficult to observe that.
Yeah, we haven't come up with an in situ method yet, but there probably would be something like that. In other words, there's also a disconnect between the surface science and us, because at this temperature, there's a significant vapor pressure of copper. So our quartz tubes actually become shiny and look like copper. And so surface scientists don't want that.
No.
So they stick to lower temperatures, like around 700, and they use other precursors than methane.
These other people's upgrade.
So this is a typical challenge in science, where they can contribute so much to our understanding of what's happening in the very early stages of growth, nucleation forward. And we don't yet capture nucleation events, which are happening with very small clusters, probably around C20 or so, because we don't have that length scale and batch experiments. We see islands, like I'm showing you now. So we also collaborated with colleagues at IBM. Uwe Trump is one of the world's experts in low energy electron microscopy. And they identified where the ions were, or the flakes, and then they used selected area electron diffraction. And in that 6-lobe structure, it sort of looks like a snowflake, they walked across lobes like this 3 times for about 10 different individual flakes, and they found that all of them, with the exception of one, were single crystal. So they have fairly broad spots because the surface of the copper is rough. And this selected area electron diffraction pattern, if it never rotates, it always has the 6 spots, and then it doesn't rotate, and then it's a single crystal in that experiment. In one case, it rotated 30 degrees, so it was a 5%. So very valuable to be able to collaborate with them. And then, perhaps of less interest to this audience, but we got moderate mobility values. So one of the great interests in graphene is carriers move at about 100th the speed of light. So the very high velocity or carrier mobility of electron holes means possibilities with very high switching speeds for electrons. So this has been scaled by a group in Korea. They used our copper growth conditions, but they wrapped a piece of copper foil into an 8-inch diameter tube furnace. And then they used a transfer technique where they used thermal tape rather than PMMA, and they're running it through a single step of roll-to-roll processing. So it's like a batch roll-to-roll, and then dissolving away the copper. Then they heat the thermal tape and release the graphene supported on a polymer substrate like PET. So they actually could get 14 by 16 inch, I think. No, 16 by 24, sorry, with a 30-inch diameter. So there's also kind of a funny story behind this, because our group had published several papers about the growth in copper. I got a lot of phone calls from journalists who were quite excited because this is now technology potentially happening. And one of them was very shrewd, the news reporter for Physics Today. He said, why if this is published in Nature Nanotechnology or units in inches instead of centimeters? I said, I never thought of that. Maybe they're telling the Americans that they want some competition or something. So. Okay, let me now switch to talking about something closely related to mechanics, which is grain boundaries. And this was a paper with Vivek Shenoy at Brown University and his student Rasin. And we actually were just exploring. So Vivek said, what's interesting to look at? And I said, I'm extremely interested in long-term possibilities for high-strength materials, where we have kilometers of this material, and we somehow figure out how to grow it so we have great covalent bonding and grain boundaries. So, I would suggest we study grain boundaries. But then we got an unexpected result that I'll briefly talk about. But I think I want to leave you with a bigger picture that if we can get significant bonding along grain boundaries, rather than just missing bonds entirely, then we're going to be in good shape in terms of strength. So you might wonder, I told you that graphite can be a very strong material, but only at the single crystal level. Graphite, the grains just kind of butt up against each other. There's no covalent bonding at all. Or they subtend, something like plate mechanics, tectonics, and then there's just van der Waals. So the individual crystals, the grains in graphite are remarkably strong, about 130 GPa, but graphite as a material is ridiculously weak. It's in the megapascal regime rather than gigapascal. So perhaps with these metal substrates, we'll be able to synthesize this material with significant covalent bonding along the grain boundaries. Now what happened here that wasn't expected is the low angle grain boundary actually ended up being weaker than the high angle grain boundary, which was more effective in terms transmission electron microscopy as well. And one of the reasons for using TEM is, of course, it gives us an atomic scale view. But I think you can envision the challenge of finding the grain boundaries in town. So my group's approach has been divide and conquer. We have relatively large grain size material. That means we look in one area, select the area of electron diffraction, and we keep moving around until we see a rotation. And we know the grain boundary is somewhere between, try to find it, and then go to high resolution. So what's been quite interesting is the assignment of misorientation angles, and they cluster around certain angles. This is just started, and it's very challenging. So understanding the atomic scale structure is something that will be heavily researched in the future, and I envision, in terms of mechanics, that there will be the use of these sorts of nano-lab manipulators inside of TEM, where you've created a defect of a certain type, perhaps by knocking out an atom, or putting a small notch at the edge, and then pulling, and seeing what happens with the mechanics, including at the grain boundaries. So this is simply showing that, indeed, in the region of the grain boundary, you'll have two sets of hexagonal spots showing that you're overlapping two grains that are misoriented by 18.5 degrees. This is a different example from Cornell Group, where they showed that because they had a very small grain size, they could use simple dark field imaging and map the grains very quickly and color code them, so they ended up with these sorts of beautiful pictures. But this was a consequence of having quite small grains. And so then you can see all the grains quickly through this dark field. This was acquired by Jinho Han in my group, and we think these are actually missing atoms, not a good thing for the spring. And I think that this sort of high resolution microscopy will be so valuable. It's actually aberration correct and needed to understand ultimately the mechanics that we're getting out of these sorts of films. Graphene is of interest as a flexible conductive electrode. So there's another myth that's developing that we can puncture like a balloon. It's thought that graphene is highly transparent. But in terms of the emissivity, the constant K, which tells us how absorbing the material is, graphite and graphene are actually quite absorbent. They have emissivity value, not emissivity, extinction coefficient. An extinction coefficient of about 2.5 for graphite in the middle of the visible, about 2 for graphene or so. But it's just because it's so thin that it, of course, is quasi-transparent. So each layer absorbs about 2.3% visible light at 550 nanometers. So a few stacked layers look very promising for transparent conductive electrodes that are compliant out of plane. So this is a great interest. Samsung is particularly focusing on scaling up the material. They are closely allied with that Korean university group that published that other paper in Nature Technology for transparent conductive electrodes for plastic electronics. So it's possible that you'll see these just within a few years on actual consumer electronics. So our group had published on that actually before they did, and Shusung Lee, a very challenging experiment, would grow monolayer graphene on copper, dissolve the copper, transfer over to quartz substrate, and then grow another monolayer and transfer that on top, and so on until he had up to 4 layers. And so in this experiment here, he's showing that it maintains a resistance that we can measure even when it's highly curved, simply applying it. And then by using ellipsometry, we could measure the transmittance as a function of wavelength and as a function of the number of layers. Now here there's something interesting also in terms of mechanics. When we transfer graphene even with the with the PMMA polymer film, we're still not perfect. So either it's already defective when we grew it, or something in the transfer is causing some cracks to appear. So in this nice sheet of graphene, we have some cracks running through that are interrupting what Shusung did was he improved upon that technique by first softening the PMMA before he actually tried to do the transfer by adding some solvent to the PMMA layer. The softening relaxed some of the wrinkles, less cracks. Then we saw a nonlinear dependence on the resistance as we added layers. So one might have thought that bilayer would be half as resistive as monolayer, or twice as conductive, but it was more than twice as conductive. We realized what's happening is if there was a crack in the lower layer, the chance of there being another crack in the next layer would be very, very small, because there were so few cracks by his improved technique. So we have crack bridging, and conductivity can be from here, through the bridge, back to here. So this was a useful thing as well. And so we find that the PMMA graphene is significantly better than single wall carbon nanotube films, but in this study, not as good as ITO. But the Korean group has now shown that they are now rivaling indium tin oxide, which is the main competitor. And partly the cost of indium and the fact that the oxides are brittle and not compliant out of plane suggests that graphene will find use, particularly in plastic electronics. So I will actually cover this in detail a little later in the day, but I wanted to show you briefly that the ultimate fraction strength has been measured by a group from Columbia University using membranes. So we'll talk about that a little later. And my group is using Bolch techniques to look at mechanics, including within without grain boundaries through the color coding and isotope grading. So let me now tell you about passivation and this fact that graphene can actually act, even though it's an amphitic, as we talked about, it can be impermeable. And this was a discovery we made by accident. And it's one of those types of discoveries when, after you see the result, then you say, oh my God, it's just so obvious. Why didn't we immediately do that? So we were trying to understand the kinetics of growth. And in our experiment, unlike the surface scientists, we don't have in situ methods of observing the growth. So all we can do in these sorts of thermal CVD experiments is grow for a certain amount of time and then stop. And take it out and look at SEM around and so on. And we see those sorts of flakes. Or we can try to stop very quickly and the flakes will be smaller, which we call them islands. We can't actually study C20, which would only be a few nanometers across, but surface scientists have been making progress in terms of what is the nucleating event. Carbon clusters or carbon atoms are zipping around on the surface of the copper. And then some special entity forms that might be a critical nucleus, might be about C20 to C24, which is recent surface science experiments. And then it starts to grow outward. And so that critical nucleation event is of great interest. So when we stopped our experiments where we didn't have a full monolayer growth, but we had these islands in different regions, we noticed with SEM imaging that we could see evidence of neat copper underneath the islands, but between the islands we saw a very rough surface, which was copper oxide. And the same thing with scanning tunneling microscopy. We did STM. Underneath the islands we saw clear steps that were the neat copper. But between the islands, imaging was very difficult because of the thick copper oxide layer. Then we realized, well, the graphene originally was grown on neat copper because we stripped the oxide with hydrogen. Remember that step? And then it passivates and doesn't allow oxygen to come underneath and make an oxide. So then we grew three complete films. And I was giving a talk at Cornell, and Ji-Woong Park's group listened and got excited about the talk, and we hadn't published our work yet. And one of Ji-Woong's students, Lola, took a penny. It turns out you have to take a penny from 1982 or earlier. Our pennies in the United States are mostly zinc pennies. So if you try to work with a zinc penny, it can even be a little dangerous because the zinc might react explosively and so on. So by using an older penny that had mostly copper, they showed that they could protect the penny that was coated with graphene for exposure to hydrogen peroxide, a very strong oxide. My group worked with 200 degrees Celsius air to look at whether oxidation would occur, where the graphene was supposed to be protecting or not. And I won't bore you with all of the analytic techniques that we use, other than to say that just to the eye, you can see examples where before and after, this is unprotected, it tarnishes noticeably exposure to 200 degrees Celsius in the air, but when graphene is coated on it, we see no evidence of tarnishing, for example. And we use techniques like X-ray photoelectron spectroscopy to show that the graphene-coated regions always remain as neat metal that didn't form the oxide, whereas the regions that were not coated, formed a clear presence of copper oxides. And the same thing with Raman. Raman can delineate the presence of, in the unprotected or uncoated regions, oxide formation from graphene-protected regions where they have neat copper. So I'd like to suggest something to you as a mechanics audience. We think that this might find application in a variety of areas where you don't want oxide formation in metals, such as in electronics. So one example is in airliners. I heard from someone from Boeing that they have copper wires that run through the carbon fiber material that is used on the Dreamliner. And that's for lightning strike protection. Now, the thing is, that copper wire has to maintain good conductivity from the outside to the core of the airplane because the fiber preformed composite that has epoxy on it is not good enough for 50 years. So they're potentially interested in coating that would stop the oxide layer from getting thicker and thicker over a 50-year period. But I'd like to point out to all of you, and this may be of interest in your modeling mechanics and thinking about mechanics, on any metal, virtually any metal, it will be possible at the nanoscale to coat with a layer of graphene. In fact, if you think you have, for example, nickel structures, but they're very small diameter, like nickel wire, even though it's a different growth mechanism where the carbon goes in and comes out when you cool down, it'll still be monolayer because the diameter is so small, you can't put very much carbon in it. So any sort of nanostructure, as long as it can survive the processing conditions, can be coated with, for example, a monolayer of graphene. So you have this sort of sausage skin effect, but the skin is very strong, potentially. And the implications for the mechanics of the nanostructure might be very intriguing versus just a neat metal that will get oxidized as soon as you expose it to ambient effect growth. So let me tell you a little bit about thermal transport. How we do this one.
If you want, you can stop
And then continue later.
yes, as you prefer. If you want, you can have 5 minutes more. But
I think I'll stop here and then in the afternoon I'll finish the materials property of graphene and segue into graphene mechanics. So maybe now's the time to take questions.
thank you. Time for a couple of questions.
Yes, so when you talk about rebounding, how much you give this business idea, how much of rebounding weakness? I theoretical strength is 130. To what extent rebounding?
Yeah, so in this study, for example, I didn't show this study, so I'll show it now. So at the different disorientation angles, you can see the drop from 130, which would be up here, down to at different strains, for example, the values shown. And so the reduction is quite dramatic.
Is this measured or?
This is purely modeled.
Purely
So at this point, we don't have anything. That's going to be very interesting. And my group is trying to do this with isotope radon, so we know we have them. And we'll have to marry that eventually to TEM to know what the structure is. And to do that TEM cleanly, so we don't damage it. Yeah. So the reduction is quite significant. Of course, some of you might be aware that the highest human-made strengths we have over significant distances are the high-strength carbon fibers. So those, as I understand it, are at 5.60 GPa now from Toray in Japan and Cytec in the United States, and those carbon fibers are used on aircraft. And so I hope that we can hit numbers like 20. There is work now that some of you might be aware of, for example, at Georgia Tech, where they've achieved a breakthrough where single-wall carbon nanotubes, when they are embedded in polyacrylonitrile and processed in a certain way, they're extruded and pulled and heated, they've hit strengths of 12 GPa